Hello statistics student, this video is for chapter 3.3.4 probability of sampling, and we finished all of the sampling calculation, meaning if we want to pick multiple samples, what is the probability of getting some all of something or the other. And you notice that we always find probability of all of something, all of the other things, but we never look at, oh, if I pick 12, like Bob in this particular case, what is the probability that 2 are good? Oh no, 2 are defective and 10s are good. So this way we would do it in chapter 4. Okay, so in the independent rule is useful when we keep on multiplying if they're all of the same thing. If they are different things, it's a little bit more involved. So we'll analyze those in chapter 4. So the last thing we want to went over is something called a rare event rule. So we already defined what is rare event. An event is rare if probability of A is less than or equal to 0.05, right? So a lot of times an event would be rare, like all 12 light bulbs are defective. That's really rare. But how does statistics use this? So the rare event rule goes like this. If under an assumption, there must be an assumption. Using this assumption, you calculate the probability of a observed event. That means these things that you have observed has happened. Notice that that's the difference between statistics probability and real probability. In a normal probability, you are calculating something that has not happened. But you're gauging or you're trying to evaluate the chance. If it's a high chance or low chance on what it is. But in statistics, we are calculating something that has happened. But you calculate it under an assumption, like assuming that it is a fair coin, or assuming, there's 80 are defective. You assume something is true, and you calculate an observed event. But this probability is very small. That means you're observing a surprise probability. And this probability is significantly less than or greater than what we typically assume. Then we would conclude that the assumption is not correct. So again, you're looking at something that happened, and you turn around and calculate the probability, and you find that this probability is very rare. So it is unlikely to occur by chance. So you would say, then we can use it to do conclusion. The two conclusions you can see is, if the chance, you're observing something that is unlikely to occur by chance, then you say there is sufficient evidence. You always use the fact that there is sufficient evidence to conclude that the change is effective. These things could not just happen by chance. Something must have changed to cause this to happen. So usually when we are the reason why we're interested in something happening is we apply some change and we look at what happened, and you calculate what's the chance of it happening. And if it is really low chance of happening, if the change is not effective, and you see it happen, that means the change is the one that caused it to happen. It's not supposed to happen by chance. Cannot have happened by chance. So the other one is, if you see something that happened, but the chance of it happening is really high, and so you would say there is not sufficient evidence. The evidence is really low because this thing could just happen by chance. Okay, and it is not caused by your change. So let's look at what we mean by doing a change. So in this particular case, we are applying a change, which is having someone take a vitamin C to see if they can reduce the common cold. So you have 56 subjects take vitamin C, they catch the cold. 6 out of 56 catch the cold. But for those that does not have vitamin C, 8 of them catch a cold. Now, and then for some reason, they would use probability to calculate, how come I have 6, now I have 8? Or actually, for those people that don't take vitamin C, they have 8 people. 8 out of 56 will catch a cold. So 8 out of 56 could be more, could be less. So if vitamin C has no effect, so the chance of having 6, because this is all sampling, right? So sometimes you would have more, sometimes you will have less. The chance of having 6 out of 56 is 32% chance. So the reason why you can have 6 is not because, maybe it's not because of vitamin C, it's just because of the sample variation. That it is just within the parameter of, sometimes you have less of something, sometimes you have more of something, and you actually use probability and calculate the chance. You will ask me, Miss Chia, how do you calculate that? We'll learn how to do this in chapter 4. So it is something that you will learn. And what about 0.32 chance? 0.32 is greater than 0.05, right? The probability is not unlikely. It is likely to have 6 because if people don't take vitamin C, sometimes out of variation, you can have 6 out of 56, 56 that has this same result. That is seems to be lower, but the chance of having such low number is 32. So it could have happened by chance rather than due to vitamin C. So our conclusion is there's not sufficient evidence to conclude that the change of having someone take vitamin C is directly causing this low number. So you do not look at just the difference. Sometimes people would just look at, oh, there's only reduced by 2, probably it's not caused by vitamin C, it's caused by sample variation. But we do not look at the differences, we look at the chance. And later on, we will actually calculate how to do this chance. The chance of 0.32 is likely to happen because it's greater than 0.05. So we would say this lower number is not caused by vitamin C, but it's caused by just chance variation. It could just be happened by chance. So the conclusion is not sufficient evidence. Not sufficient evidence to conclude that it is effective. So this is called the rare event rule. We still have some time. Maybe I'll do another one. So another one would be maybe you toss a coin. Okay, you assume the coin is fair. So if you assume the coin is fair, so if you toss 10 times, so this is the first time. So sometimes you have heads, sometimes you have tails, sometimes you have heads, sometimes you have tail, right? 10 times. It's just because it's sampling variation. What do you expect to happen? So expect the normal number is 5 head, 5 tails. Sometimes you would have 6 head, 4 tails. Can this happen by chance? This could happen by chance. And what is the more, what are the expected one that's going to happen? Sometimes you would have, sometimes you can have 1 head, 9 tail. Would this happen? Theoretically, it could happen, but this is more often, right? These are more often. This is more often. This is a really rare one. It could happen because you just toss them. So one thing that we can look at is to theoretically look at something called simulation. So in status, there is, if you click on data, you can do a coin toss generator. So this is assuming the coin is a fair, and you toss 10 times. Say for example, you toss 10 times. Oh no, right. And then you have 1 coin. Is it 1 coin? Can I do that? Yeah, 1 coin 10 times. And then you put your answer. Let me clear this first. Put your answer in here. So let's see. Oh. So you would have sometimes, so this is, I think this is the number of heads or the number of tails. I don't know. So 0 means head, 0 means tail, 1 is head. So the first time, because you're tossing 1 coin, so you have no head. They talk about like that, right? So you can count 1, 2, 3, 4, 5, 6, 7. This time I have seven heads. You can say I'm gonna toss. I'm just gonna toss it a lot of time. Pretend that I have 10 coin, right? So it actually just means that I am tossing it a lot of time. So sometimes you would have 7 heads, sometimes you have 5 heads, sometimes you have 6 heads, sometimes you have 4 heads. Do you see 1 head? No, not very rare. It's very rare, right? So this is how you can actually gauge what is rare, what is not rare. And then in chapter 4, we'll actually talks about how to calculate what is the chance of having a particular outcome. So if for some reason you observe a coin toss, your observation is 1 head and 9 tail. What would you conclude? This is really rare, right? You're not supposed to see it. We use a simulation and we see that even seven head and 3 tail, or 3 heads, 3 tails. These are pretty often that shows up, but we never see this happening. So if we see this happen, our assumption must be wrong, right? So something has happened. What did we assume? We assume that it's a fair coin. If you see something like this, you would say, we have evidence. There's enough evidence that the assumption is wrong, that the coin is not fair. And which is common sense, right? If you see someone toss 10 times and you see this, you will say that, well, your coin must be loaded. It's not a fair one. Because in a fair one, we usually see 5, 5, 6, 4, 7, 3, a lot of time, but not that extreme. So we can do it multiple times. You can see that in the second time we do the 10. So yeah, we still see 5, 6, 4. They're really common. But the third time we toss it 10 times, right? We don't see 0. We don't see 1. So if those shows up, you would know that you conclude with evidence that there's evidence that your assumption that they're fair coin is wrong. So you can say that there must be a change, and this change was your assumption. Your assumption is wrong. Okay, so either a change or an assumption. If you see something that is surprise, if you see something that's surprise, either you can conclude that the change is effective or your assumption was wrong. So that's called a rare event rule. And it's very important in chapter 7, I think it's chapter 8, chapter 7.